All right, so let's get started. So unfortunately, Eric is not feeling well today, so he asked me to give this lecture for you. By the way, if you don't know me, I'm Marwan. I'm one of your TAs in this class. So today's lecture will be lecture 6. It will be about partially observable graphical models and the expectation maximization algorithm. But before we get started, let's just go through a few logistics points. So last week we released homework 1. The due date is next week, and if you haven't started looking at the homework, it's a good time to start. So projects, just a reminder, that's a big part of this class, I guess the biggest part of the class. And we ask you to form teams of 3 or 4 people. So if you haven't found the team, I guess right now is the time to start hurrying up. So TAs, including myself, we posted a few project suggestions on the course webpage. So you can use those as hints. So you don't have to work on any of these suggested projects. You can come up with your own. But these are just as hints for you to consider which direction to take. And the project proposals will be due February 22nd, which is about 3 weeks from now. Finally, lecture 5, we had to miss it last week because of the weather conditions, and we have to skip it because the schedule is very tight. We'll just continue from lecture 6. Today, I'll just highlight a few key points from that lecture, but I encourage you to refer to the slides, and hopefully the team who scribes the lecture 5, they will scribe it based on the slides and the reading material. Questions?
Lecture 6 online?
You mean lecture 6 slides? If it's not online, the slides will be posted later today. All right, so let's get started. So let's recall from the previous lectures that we have multiple scenarios where we use graphical models. Eric discussed the directed and undirected graphical models. There are graphical models where all the variables are observed. There are graphical models where only a set of variables is observed. This is going to be the focus of our lecture, and specifically we'll focus on the directed graphical models with as a subset of variables that is unobserved. We can apply multiple estimation principles to these graphical models. And what I mean by estimation principles, given a data set and given the graphical model or a set of variables that are connected through a structure, we can try to estimate the parameters or even maybe the structure of this graphical model. There are principles that are familiar to all of you probably, which is maximum likelihood estimation, maximum conditional likelihood, and less familiar such as max margin, max entropy. We're not going to cover these. We're going to focus on the maximum entropy. Maximum likelihood estimation. In machine learning, we use learning as a term for estimation. In statistics, estimation is a more common term. But basically, by learning, we mean just learning the parameters of the model or learning the structure between the variables. So here's an example that is actually taken from lecture 5, where we would like to estimate the parameters of this simple Bayesian network, right? And by parameters here, in the case where all the variables are discrete, or let's say binary, we would like to learn these conditional probability tables. So what we can do, we can write down the likelihood of the data under this model, take the log, and get the expression on the right. And I guess one of the observations that we can make here is that everything is related, like all the components of the likelihood are related through the products. So once we take the log, everything decomposes. So we get a sum over the terms, right? Before going forward, so we'll introduce some very simple and useful notation, which is called the macro notation for plates. Instead of just writing down the IID variables and just replicating them all the time, so we'll clutter the graphs that we're trying to build. So instead of that, we'll just use these plates and we'll just indicate the number of IID variables or independent and identically distributed variables by this n number here. So as long as the variables are IID or exchangeable, we can write them down in this form. And actually, instead of just writing single variables on the plates, we can actually write subgraphs on the plates. So basically, the subgraphs will be replicated and then used the specified number of times. So now back to the Bayesian networks. So assume that we have this graph on the left. In order to estimate the graph, we can try to write down the likelihood, assuming that all the variables are observed, right? And then everything is related through product, which means that we can actually decompose the graph into smaller components, right, and estimate every single component on its own. And in lecture 5, if you look into the slides of lecture 5, you'll see that every single component, so every single structure, depending on the assumptions that we make about the relationship between the variables, let's say linear dependence or maybe discrete probability distribution, we'll have very specific methods that we can use to estimate every single component, as long as the variables are observed, right? So for the sake of the example, and just to compress the material from lecture 5, I'm not going to go through all these like GLMs and details of these other models, but I'll just give you an example of discrete Bayesian network that is represented by these conditional probability tables. And the parameters are basically values in these conditional probability tables. So our goal is to learn these parameters in these tables to estimate the Bayesian network. So we can compute the counts, right, for every single combination of variables. Let's say the parent of the node I was equal to k, and then the node I is equal to j. So we can just go through the data, the count all the instances that had this relationship between the variables, and just compute these so-called sufficient statistics, right? And then based on these sufficient statistics, we can write down the log likelihood in the following form, where we'll have the sum weighted by the counts, and then we'll get the logarithms of the parameters, right? So now we'd like to optimize this. We'd like to maximize the likelihood of the model to estimate the parameters, and to do so, we'll just introduce the constraints. We want all the probability distributions to sum to 1. We'll use this as constraints. We'll use the Lagrangian multiplier method, and we can optimize this to get the optimal parameters, right? So this is just a recap. I'm sure everyone studied this in like 601, 701 lectures. So here's an example that Eric has already considered in one of the previous lectures, which is HMM, right, or a hidden Markov model, where we have sequences of events, and we can consider two scenarios: a supervised scenario and unsupervised scenario. So recall this example with the gambler and the casino player, right? That rolls dice, and then at every step, the casino player decides whether to swap a die from fair to unfair. So we can consider the case where we observe the casino player, we observe which die the person used, and in this case, we'll get both the states, or which die was used, as well as the observations, the values that we get from the die roll, right? In the unsupervised setting, we assume that we don't observe some of the variables, or we don't observe the state. So the state is latent. We assume that there is some state. We know that there are two different dice, but we only get to observe 100,000, so say 10,000 rolls. In either case, our question is like, can we find the parameters of the model that presumably generated the data, right? And for this, we can use the maximum likelihood principle. So for now, let's just consider the supervised case, assuming that we know all the states and we know all the observations. So what happens in this case? Just as a reminder, let's just write down the hidden Markov model. To fully characterize the hidden Markov model, we need the transition probabilities, and we need the initial probabilities, the initial distribution of the states, as well as the emission probabilities. What is the probability of observing certain values given a current state? Right? So basically, we can characterize everything by two matrices: the matrix of A's and the matrix of B parameters. Right? There are some constraints. We know that, let's say, rows of the matrix should sum to 1 because these are conditional probability distributions. But other than that, we just need to estimate these parameters. So how do we estimate this? We can define two values, aij and bik, which will be the counts of the transitions between the states, as well as the counts of observations of certain values from a given state. So as long as we have a sequence of observations and we have a sequence of states, we can go and compute these counts. And omitting the algebra, just doing the algebra, we can get these values as the estimates or maximum likelihood estimates. Sure. Sorry, can you say again? Sure. Okay. Yeah. So the question is, what if x is continuous? Right now, I assume that x's are discrete observations. Let's say we roll a dice. We have 6 possible observations, right? We have 2 states, 2 different dice. If the observations are discrete, we can use the Gaussian distribution, do the same algebra and manipulation, and we'll do that next in a few next slides.
Question. In the previous slide, the I birthday of states like 1, 3, 1, always
Sorry, sir, once again, what was the question?
We should have a white change. And on state, for value of that
Right. So the question is like, what are these y's and the superscripts of the y's and the i's and j's? So basically, we one-hot encode the categorical values, right? So we can always say that let's represent our k values with a vector of 0s and 1s, and then the vector will have only a single 1, right? So these are the indices in this vector. And then by multiplying them together, you just try to count every time they co-occur. So every time they don't co-occur, basically you'll get a 0, right? All right, so the intuition here is that to estimate every single parameter of the model, the only thing that we need is just basically go and count the co-occurrences and get the frequencies from the data, right? So the question is, what is the potential downside of this estimator? Does anyone know? That's right. When someone said it's overfitting, it's actually, yeah, the drawback, the severe drawback is overfitting. If the data set is very small, there might be very unlikely events or very unlikely transitions for which the probability is still non-zero, but our estimator will just give 0. So how do we overcome this problem? So why is it very bad first, right? So here's an example. We can have this, again, casino player example where the states are all, let's say, fair dice. And after running this estimation algorithm by counts, we'll just get that the probability of transitioning from fair to fair is always 1, and then we'll never get the unfair to observe the other state. Right. So how can we solve this problem? The very straightforward solution is to use pseudo counts. So we assume that by default, without observing any data, a priori, our counts are defined by some R and S matrices. And then every time we observe the data, we'll just add these counts, additional observations, to the existing values, right? So the larger the pseudo counts, the larger the number of pseudo counts, the stronger our prior belief about certain transitions between certain states, right? And vice versa. So if we have a lot of pseudo counts, we'll impose a very strong belief. And if we have fewer pseudo counts compared to the actual observations, the belief will be pretty weak, but it'll be just a smoothing. And this is an example of something called Bayesian estimation, right? With a uniform prior and where the parameter strength corresponds to the number of pseudo counts that we add to the model. All right, so that was just an example to showcase some material from lecture 5. So actually in lecture 5 you can find the estimation principles for fully observed components of the Bayesian networks of different structure under different assumptions. So one of them is this generalized linear models that we are fortunately not covering today, but you can look it up there. Now we're going to transition to the partially observable models, right? And let me motivate it with a real-world example, which is speech recognition. So all of you are familiar with this problem. We all know that right now we can recognize speech and convert it to text pretty easily on our phones. we used to have, so the initial approaches to this problem were based all on hidden Markov models, where we assume that there is some latent state that generates this noisy sequence of speech that we chunk into different, components, and then these components of the speech are called phonemes. So we create dictionaries of phonemes, of potential phonemes for different languages, and then we're trying to basically invert infer the sequence of phonemes that potentially generated the signal of the speech. Right. Similarly, for biological evolution, we might wonder what is the structure of the ancestral structure of certain species, right, that happened over T years, and we can convert again in a graphical model and try to infer the values of the parents given the observed children. But basically, for this lecture, we'll consider a very simple example or a simplified version of this that can be used as components later on to build more complex graphical models. So here's an example of a simple graphical model where we have a z variable, which is a parent of variable x variable from x1 to x3. So in case when we observe all the variables, we can write down the log likelihood. It will nicely decompose into this structure. But if we don't observe one of the variables, and we still would like to write down the likelihood of the data, right? We'd like to write down the probability of x while not observing z, right? In this case, we'll have to marginalize out or integrate out or sum out the unobserved probability, right? So this will result in this objective in this case. Similarly, in the undirected graphical models, we can write down, as long as we have the structure, we can have the clique marginals, and basically the likelihood that we can write for the fully observable case will decompose into the sum over these clique marginals. And I believe Eric already covered that in the second or third lecture. So this is a reminder from the previous lecture about the probabilistic inference. So given a graphical model, there are multiple tasks that we would like to accomplish, or we can accomplish. So one of them is answering queries such as what is the conditional probability of one variable given a set of other variables. And to answer these queries, we use inference, or we call this procedure inference, right? So the other one is, can we infer the most plausible model from given the data under certain constraints, the constraints that are imposed by the graphical model, right? And we call this learning. From the Bayesian perspective, we can also see it as inference, right? We can say that what is the probability over the space of all possible models given the data, right? And if the probability is strictly peaked at some specific model, we can say, oh, this is the model that actually generated the data. In this lecture, we'll see that actually to learn partially observable graphical models, we'll have to iterate and iteratively solve the two tasks. And we'll come to that in a second. So I mentioned inference, and in the previous lecture, we've covered the exact inference algorithms where we can actually compute these conditional probability distributions exactly. So this is the elimination algorithm, the message passing algorithms. But in certain cases, computing the probability distributions exactly is impossible. So this will be the topic of the next module in the class, which will be based on this, which will discuss basically the approximate inference techniques, such as Markov chain, Monte Carlo, and variational inference. But the idea there is that to compute the answer to the query, we need to compute some infeasible integral, or computational infeasible integral, or summation. Anyway, so inference can be used as a routine for learning. So let's walk through a simple example of mixture models. And this is a fundamental problem in machine learning and statistics, where we're given data and would like to just to estimate what is the density, probability density, of the distribution that generated this data, right? And one approach is to represent a very complex density by a collection of very simple densities that we call the mixture of simple densities, or a mixture model. So here's an example where we have probability distribution P of x that could be multimodal or arbitrary. And we would assume that the simple densities are actually, let's say, Gaussian or some other unimodal distribution that we already know how to write down analytically and we already know how to manipulate. In this case, we can introduce a latent variable or an auxiliary latent variable z that basically will be selecting between these densities. And in essence, after we fit the model, every single component of the density will select certain subpopulation. Right? So we have these discrete latent variables that select between different density components, and then we have the intra-mode distributions that correspond to the modes of the density of the distribution. So where are these latent variables coming from? Right? There are three possibilities here. So as in this example, we came up with an imaginary random variable, with a z variable that allows us to decouple the distribution. The distribution could be very complex, but then given the z, we assume that it is unimodal. It is simple Gaussian distribution, for example. Similarly, in the speech recognition case, we assume that there are some latent phonemes, and then given the phoneme, the distribution of the speech is very simple. Right? All the mixture models are under this category. So latent variables could be other real-world objects, but these are hard to observe. So for example, temperature of a star. It's hard to observe, hard to measure. Or it could be these could be objects that are observable, but for some reason we didn't observe them because our faulty sensors, right? Just missing data. All right, so now let's consider a very specific example. Very popular Gaussian mixture model. So in this case, we'll assume that there is k Gaussians. So this latent variable z has k possible values, and it selects between k different Gaussians. So mathematically, we can write it as follows. So this is the probability of a single point under this model, where we sum over the components, the Gaussian components, and then we weight them according to some mixture proportions. Initially, we don't know, so the mixture proportions are unknown, as well as the Gaussians themselves, and we would like to find the most likely, the most probable parameters for the model that generated the data.
I want one question in the previous slide. What does subscript include n represent in this case in the first equation? X subscript n.
Right, so in this case, the subscript n in this equation denotes the nth sample. So let's say we have big N samples. We index them by small n. So subscript n is this thing. Right. So we can write it in more detail. Right. We assume that the distribution of the latent variables is multinomial, and then the conditional distributions given one of the multinomials is Gaussian with a known covariance matrix and a known mean vector. And then we can simply write the full likelihood as given on the slide. So the question is like, why learning this model is harder? On the previous slide? Okay. Previous, okay.
Yeah, it's this one. So I understand that it's normal distribution for every of the k clusters, but why do you have to multiply pi to the distribution?
All right, that's a good question. So the question is, why do we have to multiply pi k to every distribution? The reason is if we don't know which component it came from, we can't select specific component, right? So if you recall, this is the probability of the component, right? The prior probability of the z, which is this pi k. And then this is the conditional probability. So given z is equal to k, this will be the probability of x, right? If we don't know z, we have to sum over all possible z's and then just weight according to the probability.
I'm sorry, it's not all of them. So,
Okay.
what are we trying to do here? Are we trying to do this like as an iterative process, or are we just trying to find a way to kind of get the maximum likelihood?
Right, so on this slide specifically, we're just writing down the likelihood of a single point. But eventually, we would like to actually maximize the likelihood over the entire data set.
how to ensure that for all samples, the span of the input stage would be like ensure that summation by k over k is equal to 1, etc.
Yes, of course, because it's a multinomial distribution. So on the next slide, what I wrote here is that we assume that this is a multinomial distribution. It has to sum to 1. Otherwise, yeah, it's not going to be a proper distribution. All right, so the question was, why is this objective when we sum out something latent is hard? Right, any guesses? Yeah.
You do want to stand.
Sorry?
No. Well, that's hard computation, right? If it's a summation, for example, you can easily imagine the sum is supposed to be
right.
discrete functions that have long states, right?
Yeah.
And each calculation that isn't necessarily true.
True. So your answer is like it's computationally hard to estimate it compared to the other one.
Yeah, that's the better way to put it.
Right. Okay. So that's the right answer. There's one more answer. So let's say if we were to observe everything, right, our likelihood would decompose. And I mentioned that, I think, multiple times. But this is a very important property because once we decompose the likelihood as into a sum over term of the terms, they become pretty much independent. So trying to optimize them and assuming that the parameters of every single term are independent, they're untied, we can take every single component and estimate it without the other components. Basically, they are decoupled. So we can. What I'm trying to say is that basically by estimating, we can estimate the parameters of every single component, pretty much from all the data, right? So the ratio of the number of parameters number of data points per parameter becomes very high. So it's much easier to statistically estimate. So if we couple them together, it is more computationally. It's much more computationally hard. As well as everything becomes coupled. So we have to estimate all the parameters at the same time from the same data set. So the number of data points per parameter, again, becomes pretty low in terms of ratio. Yeah?
Yeah, I'm just asking for clarification for the IID setting, because you're saying that we are in an IID setting, but I'm not sure what you're referring to, because for the graphing gauge, it's directed graph, so they're definitely not independent. So where this
So the IID setting in this case is the IID sample. So let's say you sample a point from your distribution. So all the points are sampled independently and identically from the same distribution. Not the variables. So the variables are dependent. The samples, like the data points.
Okay, so you're saying that for example, for the DAG there, it's just kind of in relation to the different clusters, while the samples are like sampled.
Exactly. Yes. Samples are drawn independently. All right. So let's try to make a few steps with this Gaussian mixture model towards the actual EM algorithm. And on this slide, I'll just give you. I'm just giving you the equations for estimating the maximum likelihood, assuming that we've observed everything. So let's just pretend that we've observed the latent variables. We can write down this decomposable nice likelihood. We can estimate the parameters pi, mu, and sigma. That's a question.
Just out of curiosity, because there were some other related questions, but places where we have prior and we're estimating the probability for a single data point.
Right.
We could just iterate that, right? So for time step t plus 1, we could use the probability for time step t as a prior, right?
True. True.
That would be, so that would just extend it to ended.
Right. So your question is about the whether.
Just there were some questions about like we're doing it one data point, and you said later we're going to do it, but the whole process of doing it.
I mean, it will depend on the optimization process, right? So one way to think about it is, if we were to do, let's say, stochastic optimization of this objective, then I would say we can think of every optimization step as doing inference, given the previous step, where we can think of the previous step or the previous estimate as the prior for the next one. In this case, in the case of the expectation maximization algorithm, we'll actually be able to optimize over the entire data set at the same time. So we're not going to be doing any like stochastic optimization in this case. So these argmaxes here, for example, they assume that this is the complete likelihood over the entire data. So we do sum over all the data points, right? So now the question, what if we don't observe z? What can we do? And I already mentioned this expectation maximization algorithm, but the questions are, what is the E step, what is the M step? What is this, what do we expect and what do we maximize in this question, in this problem? So it's nice to connect it with the k-means, a very popular algorithm that you all know probably from one of the early machine learning courses, where we would like to cluster the data. Let's say in this case in 2 clusters. And how do we do this? Well, we come up with this latent variable that indicates the cluster for every data point, and we'd like to assign the most probable cluster to every data point. And the most probable cluster to the data point is the one that is the closest, whose centroid is the closest to the data point. And then we iterate between the 2 steps. We assign the data points to different clusters. So we initialize the clusters, we assign every data point to a cluster, then we recompute the cluster centers, and then we iterate until convergence. Right? Similarly, we execute pretty much the same algorithm with the EM, with the Gaussian mixture model. So we start with unlabeled data. We assume that, or basically we guess what are the mixture proportions and what are the parameters of every Gaussian component. And in this case, we guessed these 2. Then we iteratively refine both the mixture proportions as well as the positions and the shapes of the Gaussian components. But this is just a high-level overview, so let's go into the math of this. So this is just the likelihood that I already wrote for you for the Gaussian mixture, where we have proportions, where we have the covariance matrices and the mean vectors, and these are the parameters we'd like to estimate. So let's here introduce a new quantity that we call expected complete log likelihood. So this is a new thing that I will argue that this is the objective that we would like to optimize. So in this case, it is basically the complete log likelihood as if we've observed z's and x's. But then we take this quantity and we take the expectation with respect to probability of z given x, right? And in case of the Gaussian, it will take the following form, as given at the bottom of the slide, right? So on the E step, we'll try to estimate this expected complete likelihood, right? So given some fixed parameters for the Gaussian mixture model, which is pi's, mu's, and sigmas, we'll try to compute this probability of z and k equals to 1, given the data and given the other parameters. And we can do that. This is a very simple, so we'll just use the base rule. We can compute the joint probability distribution. We can compute the marginal down here. And this is essentially the inference step, right? This is the expectation, where we compute this thing and we get this quantity, the z in the angular brackets, right? At the maximization step, yeah, go ahead.
So, in polymerase textbook, when they're explaining EM, they're showing examples where we're missing some data points, right? We have A, B, C, and D, and we're missing like C and D or something. In this example, are we saying we have all our xn's, and for every instance we're missing a z term, and that's what we're trying to, and that's why we're using EM?
Right, right. That's a good question. So. In this case, we assume that we are always missing z, right? We're always missing, right?
And data points, right? And every instance is missing z.
Right, right. But there could be cases. Where the latent variables, let's say, were due to unmeasured effects of some sort. For some of them, we could have measured z, right? We could have observed it. For some of them, we didn't. So for those for which we could have observed, we have observed z, so we can do the standard MLE. For the other ones, we'll have to do EM or this type of learning. Okay, so back to the EM, to the M step of the EM. Now we have this objective. Now we can just optimize this objective with respect to the parameters, right? So I'll just take the argmax, do the math, compute the pi k star, do the same thing for mu's and the sigmas, the covariance matrices. And the only thing to note here is that as long as we computed the expected complete log likelihood, the math here is literally isomorphic to Emily. So we basically fill in the values for the z variables and pretend that we've observed them or we estimated them. And then we just carry out the standard maximum likelihood optimization. So basically, EM algorithm for a mixture of Gaussians is something like a soft version of the k-means algorithm, right? And then we can compare it side by side. So on the left side, we have the EM, on the right side, k-means. When we do the E step in k-means, we just compute argmax, which is the hard argmax over the possible values. On the left-hand side, we just compute this soft probability distribution, right? This is the multinomial probability distribution. On the M step, we just compute those with weights, tau. And here, instead of weights, we use the delta functions that indicate the hard assignments. So I argue that to do EM, we need to optimize this expected conditional likelihood. But the question is, like, why do we want to do that? Like, how does this relate to actually optimizing the objective that we care about, which is the log likelihood of the data, right? So what we care about is optimizing this log probability, where we sum out over the z variables, and this is very difficult, right? So to justify this, let's just make a step back and introduce a couple of definitions. So we'll define this log probability zx as in more general, like in any general graph where x is, let's say, all the observable variables, the z's are all the latent variables, and we'll introduce the incomplete or marginal log likelihood, right? And now we'll introduce the expected complete likelihood as a function or a functional of some Q distribution. So what is this Q distribution? This Q distribution could be any distribution over z's, right? We just assume that this is some distribution that gives us the probabilities for different z values, conditional on x's and the parameters theta, right? So it becomes a deterministic function of theta. It has a very nice property. It factorizes the same way as the complete likelihood because it's just a sum, and then this multiplier is just a weight, right? So we'll get a sum of multipliers that are multiplied by another sum. So basically, it's a huge sum of terms. And the question is, like, if we maximize this expected complete log likelihood, what happens with the actual objective? So we can apply the Jensen's inequality to the actual objective. And we see that this expected complete log likelihood lower bounds the objective that we're trying to optimize. So the question is, when is this a tight lower bound? Or is it going to be tight at all?
We observe all these.
But in this case, we don't observe, right? We're not able to observe them, right? We assume that they are distributed with respect to some Q distribution. So as we'll see next, actually, it will be tight if QZ given X is equal to the posterior distribution, or the probability of Z given X that we can derive from the complete distribution. So what happens here is that we can introduce this functional. So let's go back just one moment. This is the expected complete log likelihood. This is a new functional that we'll call the free energy, that again depends on this Q function, the Q distribution, and the parameters of the model. And the only difference is that we have this complete likelihood divided by this QZ, right? And we know since the complete likelihood plus the entropy of the Q is lower bounding our actual likelihood, we can write down the same expression here, right? And then the EM algorithm actually becomes a maximization algorithm, right? So at the E step, we're actually trying to maximize this functional with respect to the Q distribution, right? So we're trying to estimate. So when we're trying to estimate the probability of z given x, we're actually trying to optimize some Q distribution in a parametric form. And at the m step, we are fixing this Q, and we're trying to optimize this free energy with respect to the parameters theta, right? And there's a generalization of the EM algorithm. EM algorithm is actually a special case of the so-called MM algorithm, or measurization maximization, or minorization minimization. And if you look at the picture on the right, it is equivalent to the coordinate descent on the free energy. So basically, if we represent all possible distribution Qs on the x-axis and all possible parameters theta on the y-axis, we will be basically optimizing for first along the Q, then along the theta, etc. Also, there is a computational benefit of this. If you consider every optimization step as a single step and compare it with a stochastic, or sorry, not stochastic, just a gradient descent, gradient method, this algorithm will converge much faster. It will have much better convergence rate. The trick is that every step, the E step and the M step, are more expensive than just computing the gradients on the complete likelihood. So let's analyze now the E step and the M step and understand what's going on here. So the claim is that Qt plus 1, when we do the E step, is actually equal to the probability of Z given X and theta at step T. So this is what we originally did for the Gaussian mixture model with a base rule, if you recall that, right? We computed this distribution, and then we computed the expected log complete likelihood under this probability. So the claim is that this Qt that we get after optimizing this free energy is actually equal to this posterior distribution. And the math is pretty simple. The proof is pretty easy. So what we'll just write down the free energy, and we'll substitute this with the actual posterior distribution. And after some manipulation, we'll basically compute the ratio of the full probability distribution and the posterior. We'll get the prior, and just using the base rule, the term will cancel because this is the sum over the probability distribution, and the other function does not depend on z, right? So therefore, the sum over the probability distribution will be equal to 1. We'll just get the log probability, log incomplete likelihood. There is an alternative way to derive this. Instead of using the Jensen's inequality as we used at the beginning to lower bound this log incomplete likelihood, we can actually derive it directly using some variational calculus and show that, well, actually, this objective minus the free energy is equal to the Kullback-Leibniz divergence between the Q and the P of z given x. And then when we optimize this guy with respect to Q, since it is a lower bound, and if it can achieve the upper bound, right? In this case, KL will be equal to 0, and KL is equal to 0 if and only if the two distributions are equivalent, right?
Number one, also take significance of showing the Kullback-Leibniz divergence, getting that in the final step in the previous slide.
So how to get from here to there?
What's the significance of that? I understand how
What is the significance? So it's just a different approach of deriving the same thing, but instead of going through this lower bound and then trying to argue that one of them, by optimizing one of them with respect to the other, we'll get to the actual distribution, we can directly derive this equation and just show that they are related through the Kullback-Leibniz divergence. But in terms of like research questions, you can, instead of Kullback-Leibniz divergence, you could try to use other types of divergences on the distributions, and this will result in different types of algorithms.
Also, like a follow-up question. So again, in the slide, the proof f equals like summation z p logarithm of p over p z theta.
Mm-hmm.
That's also that. Could you view f as a summation of both Kullback-Leibniz divergences?
So you're saying right here, could we see this as a sum over? Technically yes, but the distribution is also with respect to x, right? So one of the distributions also depends on. So one of them is a distribution, right? So let's say P of z given x is a distribution over z variables. So the distribution above is a distribution over x and z. So technically, if you sum out z, you will not get 1. So you cannot say that this is a Kullback-Leibniz divergence with respect to the variable z. Yeah, it's a good question. All right, so in the m step, once we've estimated the q t plus 1, now we can optimize the free energy with respect to the parameters. And what happens here, we can a little bit do algebraic manipulation and get our expected complete log likelihood and the entropy term. The entropy term doesn't depend on the parameters, right? The entropy term depends only on the q function, and the q function is fixed right now at this step t plus 1. So you can just throw it away and just optimize this quantity with respect to theta, which is exactly what we've been doing for the Gaussian mixture model, right, at the m step. So again, we optimize it with respect to theta, and this is literally equivalent to MLE and the fully observable case, where we, instead of knowing the z variables, we just infill them based on this expectation. So any questions so far? I know it's been a bit fast to go through all the math, but any conceptual questions?
You just mentioned that the GMM is a special case of application of EM algorithm, and I mean, how is EM algorithm related to the graphical model? I mean, the general graphical model, like Bayesian network and MRF.
Right. So the question is, for those who are online, is how is this related? How is EM algorithm related to the general graphical models? Even though we used it for a very simple GMM case. So let me go back just a little bit to answer your question. But so I guess the answer is GMM is a very, very simple graphical model, right? We have one latent and then we have one observable variable. So the two variables are connected to each other, and one of them is unobserved. So in a more general graphical model, we have a graph where you have multiple unobserved, multiple observed variables. They are somehow related, but you can decompose them into simple components, right? As I just showed at the very beginning of the lecture, you take an arbitrary graphical model, you can split it apart, and you can estimate every single component. As long as you can represent it as something simple, something similar to this case, you will be able to run EM algorithm on a general graphical model. But it depends on the graphical model again. So the actual algorithm that you'll derive might be different. And for example, we'll go right now into the hidden Markov models, and we'll see how hidden Markov model is related to the GMM. So the EM algorithm there structurally is similar, like conceptually. But the way you do the E step, for example, you'll have to run the forward-backward algorithm, and it's slightly different. It requires, so the way you do inference for this algorithm to infill the latent variables might depend on the structure. Okay.
So in deriving this, it looks like the posterior z is independent of the parameters, right? Is that because x is a statistic for the parameters, or just the models?
Right. So we assume that there is, so when we introduce this expected conditional log likelihood, right? Sorry, expected complete log likelihood. We assume that there is some function q that is independent of the parameters, right? Exactly, it's a modeling assumption. All right, so let's get back to the HMM and now finally answer the second part of the question, the unsupervised learning scenario. In case of MLE, we've already derived the how to solve the task 1 and task 2, the inference and the learning part. But we can see that, let's say, in case of a static mixture, we can model it with one latent variable and a single observation. In case of the dynamic mixture, or if we know that there is some sort of temporal component, also sort of dynamic component in the data, And at some point in time, maybe distribution is concentrated over one component. At some other point in time, it switches to the other component. And everything depends on the latent state that we don't know. We are recovering basically the HMM model. So these are the maximum likelihood estimates that we can use by assuming that the sequence of the states is known, right? This is just the same slide that I've shown you before. Now, what happens if we don't know? Well, we can use the same principle, the EM principle. We can write down the complete log likelihood for the hidden Markov model. Now we can compute the expected log likelihood. So this guy factorizes into a sum. Now we compute the expectation with respect to this probability of y given x for every single component in the sum. And then we can keep iterating between the E and M step. On the E step, we'll be computing these expectations. On the M step, we'll be basically solving MLE, but with infilled latent variables. The difference, and to connect to your question about the general graphical models or general Bayesian networks, computing these expectations or doing the inference part might depend on the structure. So in this case, you'll have to go through the entire chain and to compute certain probabilities. And this problem will be on the homework, so you guys will have opportunities to practice. So this is the most general EM for a general Bayesian network, where we're saying that the E step is basically the estimation of this sufficient statistics, or so the expected sufficient statistics for the probability distribution that we're looking at. And at the M step, given the sufficient statistics, we can plug them into our objective and just optimize it with respect to the parameters. All right, so just to summarize the EM algorithm, there is a stable and nice way or a nice algorithm to optimize parameters of Bayesian networks with latent variables when some of the latent variables are unobserved or just missing, or we're just modeling certain things that are impossible to observe. The algorithm consists of two steps, the E step and the M step. And in both cases, we're actually solving the optimization problem, or we can see it as solving an optimization problem. Now, there are other models besides the HMM and the mixture models that also can be solved with the EM. So for example, this mixture of experts model that was pretty popular back in the day, and it is still pretty popular, that tries to model the relationship between some features, X, and the response y, or some targets. But they are related through also some latent variable z. And on the picture on the right, so we can assume that the relationship between x and y must be linear, but we don't know, it doesn't have to be linear in the entire space. So it might be piecewise linear, or certain parts of the space can one linear relationship, while other parts of the space can have slightly different linear relationship. So to model this, we need to introduce this auxiliary random variable that will be selecting between different linear models. And this is called the mixture of experts. So in this case, we can assume that there is some conditional distribution of z given x. We can model it with a softmax. We can assume that this conditional distribution is also a function of a linear function of x, right? And then every expert, let's say, is a simple regression function. And it's a simple regression function, then probability of y given x and z will be distributed according to some Gaussian, right? And we can just apply the Bayes rule to infer the posterior, right? Probability of z given x and y. So before in the mixture model, we didn't have this upper part, right? We only had from z to y. So in this case, we'll just have to always condition on x because it's an observed variable and we want to learn a conditional model. Also, another thing to note, so we used to optimize just the marginal probability distribution, right? In this case, we optimize the conditional probability distribution. But so the beauty of the EM algorithm is that it stays pretty much the same for structurally. It stays pretty much the same for any model with latent variables. So we will be able, again, to write the full probability distribution, take the expectations, and compute the expected conditional log likelihood, and do the E step to compute these probabilities of Z's, and do the M step to optimize the objective that we have here. And then to optimize this objective, well, maybe we'll have to use something like IRLS, right? Iterated least squares, right? So IRLS was actually covered in lecture 5, or was supposed to be covered. So you can take a look at the slides. All right, so we can construct much more complex and richer models if we have some sort of prior knowledge about the way that the data is related or the data was generated. So for example, hierarchical mixture of experts. Now we introduce 2 latent variables. They can be related somehow differently, but the EM algorithm will pretty much stay the same. The only difference is the way we compute the expectations and the way we solve the maximization problem on the M step. Similarly with the mixture of overlapping experts, where we don't exclusively select experts, but we assume that all the experts have to vote. There are multiple expert models, and all of them can be relevant at the same time. There are certain points that distributed, let's say, have certain response that is distributed according to expert 1, and there's a number of points that have same features but are distributed according to slightly different conditional distribution. But in this case, we can model it with a mixture of overlapping experts. So this goes back to one of the questions that you asked about partially observable data, or where some of the variables for some of the samples are completely observed, and for some other samples we don't have some of the observations. The observations are missing. So in this case, we'll just write down the full objective. That will decompose into 2 parts, right? We'll have the sum over samples that are completely observed on the left, and then the more complicated objective with the samples where some variables are missing. Let's say the variable y is missing here. So what we can do is jointly optimize this objective and optimize this one just by solving MLE, because we can do that. It's very simple. And in this case, we'll have to do the EM. So we can compute the expectation at the E step, and then at the M step, maximize everything jointly. Right. So there are variations of EM. There are many of them. So one of them is the so-called sparse EM, where we assume that we don't need to recompute the posterior probability exactly, right? We can somehow approximate that, or maybe we can throw away certain parts of the probability distribution over z's. So let's say the z variable is very large. The k is equal to millions, maybe, right? To compute this probability distribution, we'll have to go and enumerate all these million possible values. That could be pretty expensive. So, but we can assume that this probability distribution is very sparse. So given x, the probability of selecting one of these like million is very high, while the other probabilities are close to 0. So we can just eliminate that at the E step and approximately compute the expectation. There is a number of generalized versions of EM. In this case, we slightly tweak the M step. So at the M step, we're trying to solve this maximization problem, and we were trying to do this exactly, right? And in certain cases, it's possible we're able to do that exactly. But some models could be very, very computationally expensive. And in this case, we can try to just do a few gradient steps in the direction of the optimum instead of fully solving the M step. And we still will improve the model, because the model has this property. If you remember this coordinate descent in the parameter and the distribution space. So when we're optimizing with respect to parameters at the M step, we don't have to go all the way until the optimum. We can make a little bit of progress, and then again re-estimate the distribution and do a little bit of progress. So this is the generalized version of EM. There are generalized stochastic versions of EM, where the M step is also stochastic, where we don't optimize over the entire data set, but because we exploit the fact that the objective factorizes over the data, so we can compute stochastic gradients and make a few stochastic gradient steps. All right. Finally, this is just the summary of the EM algorithm. And there are some good and bad parts about the EM. So I guess the good parts about the EM algorithm is that we don't need to tune the learning rate or the step size. It's a coordinate descent. In the most simple case, we just go and fully optimize objective 1, then fully optimize objective 2, and keep iterating between the two. It automatically enforces parameter constraints, and it's really, really robust and works very, very fast in low dimensions. So it significantly outperforms the gradient descent methods, stochastic or non-stochastic. The downside is that every single iteration is pretty expensive. So to solve these subroutines, the sub-optimizations, might require a lot of computation. And in this case, we have to revert to these like approximate versions of the EM. Finally, I guess maybe one last step is yeah. I guess it'll be a little yeah. So everything that we discussed so far was trying to solve the maximum likelihood or maybe a maximum a posteriori version of the objective with the pseudo counts that as I mentioned before. But in some cases, you would like to use other types of estimation, maybe max margin or max entropy. So in that case, the algorithm might look slightly differently. Yes, that's the last slide. And yeah, do you have any questions? Nope. All right. I guess we are under time, but we've covered all the material. And yeah, I guess we'll stop here.